Hi, this is Professor Jim A. Chen at California State University, Long Beach. In this video lesson today, we'll look at the concept of domain and range for functions. A function is a rule that assigns a unique output to each input. For example, if I write f of 2 equals 4, then f is the name of the function, which also describes the action that this function does to its input. The number 2 is an input to this function, and the number 4 is an output to this function. We oftentimes think the function as a black box or some sort of machine. It does something to its input and then produces an output accordingly. For example, if I tell you that f of x equals x squared plus 4 defines a formula for a function, then what does f do to the input to produce its output? Well, we think of the input as the x value here. The function f is really just a black box or some sort of a machine that does stuff to its input, and it's going to have something that comes out of it. The actual action is described right here by this formula. What it does is it first takes the input x and square it to get x squared, and then it adds 4 to that result. When it comes out of it, it's just going to be x squared plus 4. So this is a formula that the function f does to every single input in its domain. For example, if we say, well, what is f of square root of 3? Well, we would take square root of 3 in the place of x, and then the action that it does to square root of 3 is you first square it, right? So we take square root of 3, square it, and then add 4 to that result. Well, that amounts to 3 plus 4, which is 7. A natural question to ask is, what would then be the set of all possible values we can use as an input for this function? And what would then correspond to possible output values? Here, if you draw a circle to include all possible values that we can use as input, and draw another circle that includes all possible values that we can use for the outputs, then f is this action that takes points from the input to the output by doing some sort of formula to it. This first set here is going to be called the domain, which is defined to be the set of all possible input values. The second set here is called the range, which is defined to be the set of all possible outputs associated with the inputs under the action of f. So if we go back to our previous example where the action was x squared plus 4, then the element x is the input in the domain, and its associated output would then be x squared plus 4. But x really is more of a generic value, and we can actually put in specific numbers to actually do some evaluation here. For example, in the previous case, we did square root of 3. Square root of 3 is a possible value we can use for x, and the action of f takes it to a point in the range, which is 7. Well, the question is, what other points are there in the domain? Well, the domain includes all possible things that makes this function defined. Can you think of any x value that you put into this formula that will make this expression undefined? Well, the answer is no. There is no x values that you can put into the x squared plus 4 and make that thing undefined. So the domain is the set of all real numbers. Here I'm going to introduce a few notations here just for simplicity's sake. We're going to use a bold R to denote the set of all real numbers. And we're going to use this kind of a script D here for the function f to describe the domain of the function f. And in this case, I would then say the d of f is the entire real number. What about possible outputs? If we look at the outputs, they're described by this expression x squared plus 4. Well, since we know that x squared is always going to be greater than or equal to 0, so if we add 4 both sides, we get x squared plus 4 will always be greater than or equal to 4. So we know that the range is a set of all possible outputs would then be the set of all y values such that y is greater than or equal to 4. Again, here we're going to introduce this notation of a script R for range on the function f to be the set of all y values such that y is greater than or equal to 4. If you use the interval notation here, you would write this as 4 to infinity, and inclusive on the 4 and exclusive on the infinity. Well, let's get ourselves to become more comfortable with finding a domain and a range for functions. It is not a trivial process. You kind of have to just treat it case by case. In the first example here, we have a function f of x that is a fraction, 1 over x squared minus x. You always begin by asking yourself the question, what possible x values can you put into this function f to make it undefined? Well, it is a fraction, and we know that a fraction is undefined when the denominator is equal to 0. So this function will be undefined if x squared minus x is equal to 0. Which means it should be defined everywhere else. So f is defined when x squared minus x is not equal to 0. Well, that's equivalent to say that x times x minus 1 is not equal to 0 after we factor out the common term x. So you actually have a product of two factors. This is not equal to 0 as long as any of the factors is not equal to 0. So this means that x is not equal to 0 or x minus 1 is not equal to 0, which means x is not equal to 1. That means I can write the domain for the function f to be the set of all x values such that x is not equal to 0 and not equal to 1. If you write this in the interval notations, that would be negative infinity to 0 and union 0 to 1. And then union 1 to infinity. On the other hand, the range for this function is all real numbers except 0. Now just think for a second here if there's any x value you can plug into this expression to make this quantity equal to 0. Yeah, it doesn't exist. But any other number you can actually get. Alright, now on to part B. We'll do similar things. We ask ourselves the question, when is this thing undefined? Oh, this is a radical function. We know that a square root function is undefined when the radicand, or the thing underneath the radical sign, is negative. So we can say that g is defined as long as the quantity 5 minus 2x is greater than or equal to 0. Well, this is equivalent to say that 2x is less than or equal to 5, or x is less than or equal to 5 over 2. So we can write the domain for the function g to be the set of all x values such that x is less than or equal to 5/2. And in the interval notation, I write this as negative infinity all the way to stop at 5 over 2 inclusively. As for the range for the function g, we look at the possible function values that this function g can take on. Because this is a radical and we can't really produce a negative number out of here, we could actually get a 0 out of that. So the range is all negative numbers basically. So in the interval notation, this would be 0 all the way to positive infinity. Now for part C is kind of a combination of those two concepts we've talked about. It contains both a fraction and a radical. So first let's deal with kind of the fractional portion of this. The function g will be defined everywhere except when the denominator is equal to 0. Well, that is when x minus 5 is equal to 0. And it would be defined as long as the radicand is greater than or equal to 0. So that is when x plus 2 is greater than or equal to 0. Okay, so now if you actually solve each one of those on its own, first we get x is not equal to 5, and the second here we get x is greater than or equal to negative 2. Both of these need to happen for the domain. So the domain for the function h is a set of all x such that it's not 5 and has to be greater than or equal to negative 2. But what about the range? What could possibly be the function outputs, the values that this thing takes on? Can you get a 0 out of this? Yes, if you let x be negative 2, you can actually get a 0 out of that. Can you get a positive number out of this? Yes, any x value that is greater than 5 will actually make this thing positive. You can actually get a negative number out of this as well. For example, if you let x be a negative 1, then you get positive on top and negative on the bottom. So the range for this function h is the set of all real numbers. Alright, lastly, I want to make one note about why this concept of domain is so important. In real-life situations, we often use functions to model behaviors or trends that sometimes only work for a limited set of values. For example, if you're a stock market trader, you like to try to model the behavior of the stock market behavior over time It may be the case that in the first few months or 3 months or so, the data actually follows some sort of a linear trend like this. But after a while, maybe some sort of a dramatic incident happened. It dropped down to here, and ever since then, it started to go downhill from that. So then there's another linear trend that you have to use to follow it. So you can only say that the behavior, the function behavior, follows this first function f over this time interval, and after that it changes to a different behavior, which is modeled by the function g on this time interval. So it's very important that you specify where this function formula actually works for the data that you have, and the data point being the input values.